At 40 degrees Celsius, the rate of reaction is the ratio of the circumference of a circle to its diameter times as fast as it is at 20 degrees Celsius. Determine the activation energy for the reaction. So right away we can tell that we're going to be using the Arrhenius equation because we have an activation energy, we have temperature, and we have something that tells us a little bit about the rate constants. So the Arrhenius equation looks like this. We have ln of K2 over K1 is equal to the negative of the activation energy over the gas constant multiplied by delta X, our change in temperature. So we know that T2 is equal to 40 degrees Celsius. And if we convert it into units of Kelvin, which actually pretty much all of our equations in first year general chemistry, you want to convert your degrees Celsius to kelvins. And to do that, you simply add your degrees Celsius plus 273. So 40 degrees Celsius is equal to 313 Kelvin. Our T1 is 20 degrees Celsius, and that's equal to 293 Kelvin. We also know that the rate of the reaction is the ratio of the circumference of a circle to its diameter times as fast as it is over this temperature range. So our K2 over K1 is simply going to be equal to pi, right? Because the definition of pi is the ratio of the circumference of a circle to its diameter. So K2 over K1 is simply pi. And from here we can simply plug in all of our values to solve for activation energy. So when we rearrange to solve for activation energy, we get that the ln of pi divided by our delta X, so 1 over T2 is 313 Kelvin minus 1 over 293 Kelvin multiplied by our gas constant R. So we know that the gas constant is equal to 8.314 joules per mole Kelvin. And this is going to have a negative coefficient because we can simply divide the implied -1 here to the other side. So after inputting this into our calculator, we get a value of an activation energy equal to 43,641 joules per mole. And we know that it's in units of joules per mole because the kelvins are going to cancel out, right? If we do this, what's inside the brackets here, we're going to get a unit of Kelvin. And on the numerator, we have an inverse of Kelvin. So the kelvins will cancel out, and we're left with units of joules per mole.